Continuing on with section 2.1 matrix operations, now we're going to look at matrix multiplication. This is unfortunately quite a bit more complicated than the addition and subtraction were. So let's go ahead and see how this goes. So we're going to start with a simple case here, the matrix 1, 2, 3, 4 times the matrix 5, 6, 7, 8. Now, what would be great is if you could just multiply the individual elements, 1 times 5, 2 times 6, and so on, that was it. But unfortunately, it's a lot more involved than that. Now, here's how it's going to work. What you're going to do is you're going to take the first row of the first matrix and the first column of the second matrix, and you're going to calculate the following. You're going to multiply the first numbers together, you're going to multiply the second numbers together, and you're going to add them up. And that gives you 19. And what that is, that's going to be the first number in the answer matrix. And again, this comes from first row, first column. And that is why the answer goes in the first row, first column here. And then we go to the next one. If I want to do, say, the first row and the second column, I would do 1 times 6 plus 2 times 8 is, let's see here, 22. And that's going to go in the place of the first row, second column. And then I do this again here. I look at the second row in the first column. 3 times 5 plus 4 times 7 is 43. That goes in the second row, first column. And lastly here, if I do the second row and the second column, I'd have 3 times 6 plus 4 times 8 is 50. And so this would be the answer of your matrix. Now the thing is, this doesn't always work. It only works if the number of columns in the first matrix equals the number of rows in the second matrix. And the reason why we need this is because if you see here, when we took our numbers, we had to have 1 times 5 and 2 times 7. So the 1 was right here, the 5 was right there, and the 2 and the 7. So I need to have the same number of numbers here to multiply by the same number of numbers there, which is why the number of columns in the first matrix has to equal the number of rows in the second matrix. Let's do another example here. Let's do 1, 2, 3, 4 by 5, 6, 7, 8, 9, 10, 11, 12. And so let's just check our sizes here. This first matrix is a 2 by 2 matrix, and this matrix here is a 2 by 4 matrix. And as long as your numbers in the middle here are equal, then that means you're allowed to multiply. And if that's the case, the answer, the size of the matrix of the answer is going to be those two outer numbers here. So that means it's going to be a 2 by 4 matrix. And then we just quickly work it out here. 5 plus 18 is 23. 6 plus 20 is 26. 7 plus 22 is 29. 8 plus 24 is 32. 15 plus 36 is 51. 18 plus 40 is 58. 21 plus 44 is 65. And lastly, 24 plus 48 is 72. Now, what if I had done things in a different way? What if I, for example, had put the 5, 6, 7, 8 matrix first? Well, we have a problem here. Now I have a 2 by 4 matrix next to a 2 by 2, and I look whether or not the inner parts are equal. Those are not equal, and so once again, can't do this. There simply is no way to get an answer here. So once again, we say this is undefined. So it's important that not only do you follow the right steps for multiplying matrices, but if they're written in the wrong order, it might completely change how you do the problem and whether or not you even can do the problem. So it's something to be really careful with. With all of this said, I showed you guys how to put matrices into your calculator, and your calculator can multiply these as well. So let's say you had already put things in your matrix A, matrix B. You just type in matrix A times matrix B, and it will give you the answer. So it will just do everything for you. So I'm perfectly fine with you doing that here. It's still something that you should know how to do by hand, of course. However, what we just saw here was a very important fact that in matrix multiplication, if you multiply A times B, it's not usually going to be the same as B times A. Now with regular numbers, this is not true. Regular numbers, if you multiply them in either way, you're going to always get the same answer. But for matrix multiplication, it's not commutative. And that's a very important fact. Usually, it's one of the first things that students see that turns out that is not commutative, that you can't just switch the order whenever you feel like. It turns out later on in math, there's a lot more things that are not commutative. But for right now, this is like usually one of the earliest ones people see. Okay, so we'll move on to the last part of the operations. The last thing that is in section 2.1 is the transpose. This is a pretty straightforward concept here. So let's say my matrix A was 1, 2, 3, 4, 5, 6, and I want to find what's called the transpose of this. So first off, to indicate transpose, we put a little capital T in the upper right hand corner, and all this means is everything that previously was a row is now going to become a column. So I would have 1, 2, 3 down here. The second row is 4, 5, 6. I'm going to have 4, 5, 6 down. And that's just transpose. So what if I had matrix B is 1, 2, 3, 4, 5, 6, 7, 8, 9. And I wanted to find B transpose. 1, 4, 7, 2, 5, 8, 3, 6, 9. And again, you see I'm just swapping all the rows into columns and vice versa. That's pretty much all there is to know about transpose. There are a couple of properties here. For example, if you transpose a matrix and then transpose it again, you get back to itself. Another one that's kind of interesting is if you're multiplying two matrices and transpose them, you can transpose each individual matrix and multiply them, but you have to reverse the order. So just an interesting little fact here. I'm not spending much time on transpose because we're hardly ever going to use it in this class, but it's still something in the book I thought I would mention.